There's little Q-tips if you want to clean them. Like if you want, because there's the worksheet that the Google Doc. So no, not the sorting. The Google Doc is just the numbering, trying to organize things by size. And then there's a printout for when you watch Cosmos, just to follow along. So if you want, I can print it out. But if not, you can just use Cami. Okay? Just trying to save paper. Alrighty, cool. Organic people, there are little Q-tips, guys. I can get alcohol if you want to like clean it, sterilize it. Actually, you can just use the stuff that's on here. Same idea. It's the sanitizer. Yeah. All right. So organic people, I want to give you guys some notes today. This is start you guys off before you start learning the basics of organic chemistry. So, what I wanted to do. All right. Yesterday we talked about atomic structure, and I want to use that as a jumping ground to talk about two different types of bonding, because one bonding is going to be really important for organic chemistry. So when we were talking about atoms, we were talking about things like sodium. So sodium, for example, has 11 protons in the center of its nucleus. I got to see what its atomic number is for us. I think it's 23, but I could be wrong. Sodium. Check atomic number. Mass. Yes. Its atomic mass is 23. So since its atomic mass is 23, that means that the neutron number is 12. Are you guys okay with how I got that? 11 plus 12 is 23. So that's the atomic mass. The atomic number is the number of protons because that's unique to the element. So that is 11. So when we were talking about things like sodium, we have the nucleus, which has our positive and negative our positive charges and our neutrons. We have to have some neutrons in there because it does not like having all those positive charges next to each other. It will repel. The other thing is our electron shells. So 2 go in the first shell. 8 go into the second shell. 1, 2, 3, 4, 5, 6, 7, 8. And then this has 11. So right now I have 2, 4, 6, 8, 10. So I need one more shell for my sodium. And now I have sodium, the atom, drawn. Good so far with that? All right. I'm going to draw another atom. Just to kind of give you guys an idea of what is happening when we're talking about ionic compounds. I should actually look up a periodic table on this. Table. Because I want chlorine. Then that's table salt. I should just look up chlorine. There we go. Okay. Next atom I'm going to draw is chlorine, so we have 2 to compare. So chlorine has the atomic number of 17 protons. Neutron number, how many do you got? 2, 4. Just forgot how many neutrons it has. Neutrons can vary, depending. Either 17 or 18. I'm going to go with 18. So what I mean by that, in case people are like, what are you talking about, miss? So the neutron number can vary a little bit with atoms. That is okay. We call those isotopes. So there's different versions of that atom. So when it comes to chlorine often has 18 neutrons, but it can have slightly less, like 17. And that's still fine. So you find it at different percentages in the environment. So don't stress out about that. Are we good? All right, so that's the isotopes. You'll learn more about that, like I said, in year 13. So chlorine's over here, and if I have 17 protons, I have 17 electrons. So that means 1, 2, next shell, 8, 1, 2, 3, 4, 5, 6, 7, 8. And then how many go in my last shell? 2. How many do I have left?
8.
I have 10 so far. So I need, and it's 17, so I need 7 more. 1, 2, 3, 4, 5, 6, 7. All right? That is chlorine, Cl. Yeah. All right. One of the, hey, if you want to talk, go in. You can go into the breakout space and work in there. All right. Something to keep in mind about atoms and stability is that they want a full shell, so they're going to become ions in order to do that. So they're going to gain or lose electrons. They're going to do whatever is simple as possible. So in this case, it has 1 electron in the outer shell, so it can lose 1 or it can gain 7. It's going to lose 1. This guy over here has 7. It wants to get to 8. Easiest way for us to do that is to gain 1. Otherwise, you have to take away 7 electrons for it to go down 1 shell. Are we okay with that so far? Is it locked? There you go. All right, so the thing we have to remember is we cannot create or destroy matter. So if these ions are forming, they need to form with something else, so that way the electrons have somewhere to come from and to go. So if sodium here is going to lose 1 of the electrons to go down a shell level, it needs to go to another atom that's going to gain those electrons. So in this case, the electron from sodium would go to the chlorine. So this would lose an electron, and then this one would gain the electron. When that happens, we know that there's there's an unbalance with the charge, and so sodium now becomes Na+, the sodium ion, and chlorine becomes chloride, slight name change, Cl-. Are we good so far with that? All right. Since these guys are opposite charges, they're going to be attracted to each other because opposite charges attract. And when it does that, it forms an ionic bond. And what's going to happen is that they're going to come together and form a compound, which is sodium chloride. And we call that an atomic compound. Sorry, an ionic compound. Are we okay so far? Now, these can obviously form in a lot of different ratios depending on the charge. So, for example, if I had something like beryllium, yes, beryllium, which has a positive 2 charge, it wants to get rid of 2 electrons, it would then need 2 chlorine atoms to take each electron to then balance to 0. So if I have beryllium and it has 2 valence electrons it's trying to get rid of, it's going to give 1 electron each to the chlorides, like that. And so that would form beryllium chloride. Got me to backtrack? Okay, backtrack. I'll go on to a new page. All right, so beryllium in the periodic table is 3. I want to say? Yes. No? Let me see. Beryllium. Hello. Okay. Beryllium is, 4 in the periodic table. So 4 protons. I'm pretty sure it must have 4 neutrons. It's usually the same number when they're small. 1, 2, 3, 4. All right? So for this guy to become stable, the easiest way for it to do that is to lose 2 electrons. All right? Are we okay with that? So what that means is if I have a chlorine atom here and a chlorine atom here, and they already have 7 electrons in their outer shell, then what's going to happen is beryllium's going to give 1 electron each to each of the 2. Forming beryllium chloride. Does that make more sense now? So beryllium has 2 electrons to get rid of, but chlorine can only take 1. So we need 2 chlorines, so each chlorine takes 1. So just to kind of crash course on ionic compounds, this assessment is very much not on ionic compounds. I just figured I'd go over it just to kind of talk about it briefly. It also gives me a good indicator that we need to cover that better in the junior school, because you guys should have known that. All right, we okay? All right, so the big thing that I want to talk to you guys about today, though, is about another type of bonding, which is covalent bonding. So covalent bonding, there's another option with what atoms do in order to form stability. So let's say, for example, we have nitrogen, and nitrogen has the atomic number of 7, and 7 protons. I'm pretty sure it also has 7 neutrons because its atomic mass is normally 17. And it has, if we had 7, 1, 2, 3, 4, 5, 6. Oh, 1, 2, 3, 4, 5, 6, 7. Yeah. Okay. 1, 2, 3, 4, 5. So that's nitrogen. Now we know that nitrogen can form ions. That is possible. It can it can gain 3 more electrons to then have a full outer shell. But it can also do something else, which is sharing electrons, which is really, really helpful. So for example, let's say we have hydrogen. Hydrogen, we know, only has the 1 valence electron and the 1 proton in the center. And in order for it to have a full shell, it needs 1 more electron. Now, it could do a transfer, but another thing that could happen is that they share the electrons. So say, for example, I have a hydrogen atom that comes by, like that. And it's sharing its electrons with nitrogen. So here's my hydrogen. Now, hydrogen has its 2 electrons because it's sharing it, and then nitrogen also takes in its hydrogen. So you see how nitrogen has gotten another electron and hydrogen has gotten another electron, but they haven't actually given one away or taken one from each other. They're sharing it. And this sharing process we call a covalent bond. So that's sharing electrons versus transferring electrons. There's when we talked about ionic bonds. That's the attraction between the positive ion and negative ion. So different types of bonds. All right. Shall I move that one off? Put that one back? I want this one. So ionic, I should say, ionic bond. So ionic bond, it's the attraction to the positive the positive ion, the cation ion, and the negative ion known as the anion. So that's one type of bond. And then the one that we're going to be talking about in organic chemistry is the covalent bond. Like chemistry 101. It's letting me know that in the junior program we need to cover this book, though, because if you guys don't know this, then it means that the junior program is not doing as well as it should. I'm not stressed if you guys know this because this is stuff that we'll cover in level 2. But I just want to show it to you. I think I put the videos up online. I just haven't linked it on the classroom.
Yeah, that's why I had to go to YouTube. It's okay.
Right, ready for me to move it? Okay. So this is the one that I am stressing today. So do you see how hydrogen's now happy? It has 2 electrons, which is what it wants to do for stable. Nitrogen now has 1, 2, 3, 4, 5, 6 in its outer shell, so it needs to do some more covalent bonding in order to get to 8. So it needs another 2 more. So another hydrogen would come over here, buddy up, overlap its shell like that. And then again, it would do that 3 times. Like that. So what this means is when I'm thinking about nitrogen as an element, the nitrogen, because of the number of spots it needs, because it has 1, 2, 3, 4, 5, it has 3 spots for bonding. 1, 2, 3. Need to grab a different color. All right, move it down. Okay. Now, I said that there is a potential that nitrogen might be a life building block depending on the species and the organism and the planet and things like that. Nitrogen isn't the best option. We know that carbon is because carbon allows for 1 more bond. So when we do the carbon atom with the atomic number of 6 and we draw it out as an atom, it has 1, 2, 3, 4. Actually, I should spread it out more. No, that's fine. Okay. So 1, 2, 3, 4. So with carbon then, it needs 4 more electrons to be stable. So it's going to be able to then have 4 more things bonded to it. So think about the overlapping. So it can overlap with that one, overlap with that one, overlap with that one, overlap with that one, and we get 3 atoms attached to it. Or sorry, 4 atoms attached to it. So carbon can have 4 things bonded to it. It's the maximum that you can have bonding pattern-wise in that case. So that's why carbon is such an essential building block to life. And as I was trying to mention very briefly at the end, when we look at the periodic table, can I move it? So let me just show you the periodic table. So the periodic table follows lots of patterns and trends. One of the trends is that when you go down a group, the group here all ends with the same number of electrons in its valence shell. So this group 1 is going to have 1 valence electron. This one's going to have 2. So both beryllium and magnesium end with 2 electrons. If you don't believe me, you can draw the atomic structures. The center stuff we don't worry about. This is group 13. So that one, 3 valence electrons, carbon 4, nitrogen 5. Sorry, this group 5, 6, 7, and then full shells stable. So these are noble gases. They're very unreactive because they are already stable to begin with. Now, I said nitrogen potentially could be a way that life is organized, but it doesn't have as many bonding as carbon. So we are carbon-based life forms. Carbon is the smallest atom that has the ability to do 4 bonding. The next one down on the periodic table is silicon. So there is a lot of belief that potentially life could be silicon-based, because it also can do that 4 bonding and make those big structures. The thing about silicon is that it is a bigger atom, and so we find it in a smaller frequency in the universe. So it's harder to get a hold of. So it's less likely. Most likely what you're going to get is carbon. Let me just show you some organic molecules. We'll just do a Google search so you can see them. But when you go looking through it, there's lots of different options in how you organize. That is not very well pixelated, pretty badly. You see how there's a lot of different options in how you bond things. Again, lots of different ways on how you bond things, because carbon can do lots of different shapes. And that's really useful for when you're trying to build living things, because you can have lots and lots of variety. Lots of different structures. See? Lots of different choices. More different choices. Even more choices here. See? Lots. So that's why it's so essential. And that's why we spend a whole area of chemistry called organic chemistry studying this. Organic chemistry is probably going to be one of the most important chemistries you'll learn if you're going to go onto any of the health science pathways, med school, that sort of stuff. You do have to take a 100-level organic chemistry paper at university. You also have to take quite a few biochemistry papers, which is going to have a lot of organic chemistry in it too. So that's why I wanted you guys to do this as your external. What else did I want to say? I think it's something like 90% of all molecules are organic. So most of what you deal with is going to be organic molecules anyway. So it's good to know. Anyway, that's my spiel for today. I wanted to just give you an overview of that so you have that background knowledge so you know what we're doing when we're designing our molecules. So next thing I want you guys to do is some organic chemistry SciPad pages just to kind of get some idea of what the language of organic chemistry looks like. Sound good? And that's us.